Okay, so having discussed the introduction, discussed the introduction and having reviewed the random variables, we now move on to a discussion on the classical detection and estimation theory. Now, we can model a detection problem. We can model a detection problem with the help of these basic components. We will have a hypothesis. We will have a hypothesis source of hypothesis. So I'll first draw this model and then we will discuss each block in some detail. And the hypothesis source will give out any one of two hypotheses, or maybe more than two. For the moment, let us say two hypotheses, any one of these two hypotheses. And this passes through a probabilistic transition. It passes through a probabilistic transition mechanism. Let me write it fully. Probabilistic transition mechanism. It passes through a probabilistic transition mechanism, and the resultant output defines an observation space. The resultant output defines an observation space, and a decision rule is used on the observation space, and a decision is arrived at regarding which of the two hypotheses were true. So as per this model, which is a basic model with which we will understand the detection theory, the classical detection theory, there is a source of hypothesis which is either H1 or H0. We don't know a priori. And the hypothesis passes through a probabilistic transition mechanism, and the output of that transition mechanism is used to form an observation space, or an observation space is derived from that. And there is a decision rule is formulated which looks into this observation space and takes a decision as to whether H1 or H0 was the hypothesis, which was given out by the hypothesis source. Now let us delve into these blocks in some detail and try to understand what are these blocks actually in a real situation. Now example of a source, hypothesis source, rather the easiest to understand, or the example, what is a hypothesis source? It's the easiest to understand in this block diagram. It could be a binary communication system, the information source of a binary communication system, or the transmitter of a binary communication system. So hypothesis H1 would mean that symbol 1 was the output of the source, and hypothesis H0 would mean symbol 0. So whenever the symbol 1 is the output of the source, it means that the hypothesis was H1, and whenever symbol 0 is the output, it means that the hypothesis was H0. A second example is that of a radar. So H1 hypothesis, H1 refers to the presence of a target, and H0 means there is no target, or the target is absent. So whenever there is a target, the hypothesis H1 or if the source gives out hypothesis H1, it means the target is present, and if it gives us H0, there is no target. Another example, possible example, is that of an ECG signal you can have H1, there is some ailment in the subject of which we have the ECG signal. H0 means no ailment. And a last example is that of speech. If we have the speech signal, H1 could be the speech belongs to a male subject. H0 could be the speech belongs to a female. And we can have more than two hypotheses here. As an example, H2 could mean that the speech is in English language, and H3, it is not English. So this is a case where you can have four hypotheses. So from this speech sample, you can arrive at these hypotheses. So you may say it is a male who is not speaking in English, or you can say it's a female who is not speaking in English, and so on and so forth. So these are the examples of sources of hypothesis. This is how we can have hypothesis. This is what is represented in general by this basic block. Now, to understand the second and the third, of course, decision rule and decision we will discuss later because it's more involved, because that is the crux of the detection problem. So to understand the second block, that is the probabilistic transition mechanism, we take a more specific example. I will take the case of a binary source of information. So binary information source. Hypothesis H1 means the output is +1 during a signaling interval, of course. Hypothesis H0 means the output is -1 during a particular signaling interval. So you don't have a priori knowledge of this. You know it is any one of these two, but you don't know which one it is during a signaling interval. And this passes through a channel wherein noise gets added. So N is the noise random variable which gets added to whatever was transmitted. So if it was +1 that was transmitted, hypothesis H1, noise gets added to that. If it is -1, noise gets added to that, and you end up getting R, the received random variable. Now this random variable, the received random variable, is the one which is used to define the, so this defines the observation space. This defines the observation space. And this, the noise random variable which gets added, this is the cause of the probabilistic transition mechanism. It's called as a transition mechanism because, for example, if 1 was transmitted, if hypothesis H1 were true and +1 was transmitted, the N which gets added could be such that N is equal to say -2, which means that +1 -2 gives -1. So there is a transition happening, and R would end up as -1 if N is such that +1 becomes -1. So there is a transition happening within this when there is a noise random variable which gets added. So this is the one which causes the probabilistic transition mechanism. Now this, for our convenience, for our discussion, further discussion, this need not necessarily be the case always. It's just an example to understand this further. Let's say that the noise random variable has a probability density function like this: small p probability density function, PDF, small PDF, probability density function of the noise random variable is like this. Let's say it takes on a value 0 or +1 or -1. It's a discrete random variable, so to say. This need not be the case always. And let's say that probability of N taking a value 0 is 1/2, and probability of n taking a value plus 1 is 1 by 4, and probability of noise taking a value of minus 1 is also 1 by 4. So you can see that if you add it up, you get 1. And based on our discussion in the last video, the PDF, since it is a discrete random variable, the PDF will be like this. So if I have to be more specific, this will be 1 by 2 delta n. This will be 1 by 4 delta n minus 1. This will be 1 by 4 delta n plus 1, which I will not write here. And now what happens is, we can characterize R now, because you know the noise random variable and you know the output given out by the binary information source, which is either plus 1 or minus 1, corresponding to hypothesis H1 or H0. So to characterize R, what we do is, let us first assume that H1 is true. Let's say that H1 is true. That means, let us say that the binary information source output is plus 1. Now, since noise can take these three possible values with corresponding probability, that is, it is either 0, plus 1 or minus 1 with a probability of 1 by 2, 1 by 4 and 1 by 4 respectively, we can write that when H1 is true, R is equal to plus 1 plus noise. Plus 1 plus noise. That will be, there are three possible values. So R itself can now take three possible values when H1 is true. Which are those three possible values? N is 0, means this becomes plus 1, and N is 1 by 4, means, sorry, N is 1, means this becomes 2, and N is minus 1, means this becomes 0. So there are three possible values which R can take when H1 is true. And R takes a value of 2 when N is equal to 1. So that means the probability of R taking a value of 2 when H1 is the hypothesis is given by 1 by 4. So given H1 is the true hypothesis, R taking a value of 2 is when N takes a value of 1. So probability is 1 by 4. So what I write here in this column is the probability of R taking these values. And R becomes 1 when N is 0, and N is 0 with a probability of 1 by 2. And R is 0 when N is minus 1, and the probability is 1 by 4. So we now have the probability distribution of R given H1 is the true hypothesis. So a conditional distribution of R is available with us. Similarly, we can form a conditional distribution of R when H0 is true hypothesis. This is what happens, and without much explanation, I can straight away write this, wherein this stands for the three possible values which R can take. R takes 0 whenever N is plus 1, R takes minus 1 when N is 0, R takes a value of minus 2 when N is minus 1, and the corresponding probability is this. So we have now with us effectively, we have with us the conditional probability of R given H1 is true, conditional probability of R given H0 is true, and we can now plot these conditional density functions just as we plotted the density function of N. We can plot the conditional density function. So let me first plot P density function, so small p, density function of R, the random variable R, given H1 is the true hypothesis. You can see that it is either 2, 1 or 0. So 0, 1 or 2. This is the random variable R. And the probability of it taking a value of 2 is 1 by 4. So there is an impulse of strength 1 by 4, an impulse of strength 1 by 2 and an impulse of strength 1 by 4. This is the conditional density function of R when H1 is the true hypothesis. Likewise, we have a conditional density function of R when H0 is the true hypothesis. When H0 is the true hypothesis, which will be, it can take value 0, minus 1, 2, 0, minus 1, minus 2, with probability 1 by 4, 1 by 2, 1 by 4. So now we have understood what is the probabilistic transition mechanism. That mechanism results due to the noise which gets added, and from R we form the observation space, and in this specific example the observation space will be one-dimensional and this will be our observation space. So we will signify the observation space as Z. So our observation space is this. So I will write here, this is the observation space, and the observation space is one-dimensional, and what it shows is actually the possible values which R can take. Now from these two we see that R can take, when H1 is the hypothesis, R can take value 0, 1, 2. When H0 is the hypothesis, R can take value 0, minus 1, minus 2. So the observation space is complete when we show these points. So this is our observation space, because this space gives us all the possible values which R can take. Now we have to use a decision rule, and using the decision rule from this observation space we have to declare whether H1 was the hypothesis or H0. Now again, as I said, the decision rule we will arrive at later. Let us first familiarize ourselves with these key basic blocks of a detection problem. Now we will move on to a slightly more complicated case wherein our observation space will be two-dimensional. It can be n-dimensional in general, the observation space. As you saw in this case, it was just one-dimensional. We'll take a slightly more complicated case. Now in this case, we will stick to a binary source of information. We'll stick to a binary information source, which will be our hypothesis source. And being binary, there will be only two hypotheses, either H1 or H0. But the difference is that in this case, the coding is such that, encoding is such that when H1 is the true hypothesis, which could be bit 1 and H0 bit 0, when H1 is the true hypothesis, two symbols are transmitted. So it is plus 1 followed by minus 1, and when H0 is the true hypothesis, minus 1 followed by plus 1 is transmitted. And in the course of its propagation, noise gets added, and now since there are two symbols transmitted per hypothesis, two samples of noise are required. N1 gets added with the first one, N2 gets added with the second one. So for example, if H1 was the hypothesis, N1 gets added with plus 1, N2 gets added with minus 1. Similarly here, minus 1 and N1 is added, plus 1 and N2 is added. And this results in the reception of two random variables R1, R2. And with the help of this we form the observation space, and clearly R1, R2, since you have two random variables, your observation space will be two-dimensional. Now let's say that N1, N2, these are independent, N1 and N2 are independent noise random variables, and let's say they are identically distributed. So be it N1 or N2, the probability density function is like this. It is same as what we had earlier. taking on values 0, plus 1 or minus 1. One by 4, 1 by 4, 1 by 2 probability. Impulses. These are impulses. So what I have written here are this strength of the impulses. And this is what gets added. So now we can say that what gets added to this is, so when H1 is the hypothesis, a vector is transmitted, plus 1, minus 1. When H0 is the hypothesis, another vector is transmitted, minus 1, plus 1. So we will represent it as vectors. And the noise which gets added can also be expressed as a vector, n1, n2, with 2 elements in it. And what is received is now a vector R. Now what happens is, when H1 is the hypothesis, the received vector will be R1, R2. Received vector will be R1, R2, which will be equal to plus 1, minus 1, plus n1, n2, which is quite obvious. Now, n1 and n2 being independent, statistically independent of each other, they can take, there are 9 possible combinations. So, for example, 0, 0, 0, minus 1, 0, plus 1. Like that, 9 possible combinations. You can work them out. There are 9 possible combinations. In fact, 3 raised to 2, that's what it is, 9 possible combinations. So I will not list down all the 9 possible combinations. But what I will do is, I will plot here the conditional density function of R given H1 is the true hypothesis. The conditional density function of R given H1 is the true hypothesis. You can plot it yourself. I will not show how I arrive at each value. Just to give an example, when n1 and n2 are 0 each, R will take a value plus 1, minus 1. When n1 is plus 1 and n2 is 0, you will get it as 2, minus 1, and so on and so on. So like this, you have 16 possible values. Now, 9 possible values. These 9 possible values we can show in a 2-dimensional space with R1 and R2 as axis, and we can show the 2-dimensional density function, conditional density function of R given H1 is the true hypothesis. So I will show that here now. You have to verify for yourself how these values are actually arrived at. So this is R1, R2, and I am going to plot here the conditional density function of the received vector given H1 is the true hypothesis. So there are 9 possible values. These 9 possible values are, you can verify 0, 1, 2, that is R2 0, R1 0, R2 0, R1 1, R2 0, R1 2. Similarly, R2 minus 1, R1 is 1. So you can see this point is R1 1, R2 minus 1. R1 is 2, R2 minus 1. And then you have R2 minus 2, R1 0. Of course, this is R2 minus 2, R1 0, R2 minus 1, R1 0. And then you have R2 minus 2, R1 1, R2 2, R2 minus 2. These are the 9 possible values when H1 is the true hypothesis. Remember, when H1 is the true hypothesis, plus 1, minus 1 is transmitted, and noise which gets added is this. And you can see these are 9 possible values. Now, I will just join this to form a grid. It's only for ease. Remember, these are the points which represent the received vector, and each of them will have an associated probability. For example, if R1 has to be 0 and R2 has to be 0 when H1 is transmitted, when the hypothesis is H1, if R1 has to be 0 and R2 has to be 0, you know that R1 or this N1 has to be, if this has to become 0, N1 has to be minus 1, and if this has to also become 0, N2 has to be plus 1. And from the PDF which I had here earlier, you can see that the possibility of that happening is N1 becoming minus 1 is 1 by 4, N2 becoming plus 1 is also 1 by 4, and if these events, these are independent events, if they have to happen simultaneously, that is N1 being minus 1 and then N2 being plus 1, the probability is 1 by 4 into 1 by 4, which is 1 by 16. So you can show that, you can show here an impulse of strength 1 by 16. Now similarly, if R1 has to be 1 and R2 has to be 0, when H1 is true, R1 has to be 1, means N1 has to be 0, and R2 has to be 0. When H1 is the hypothesis, then N2 has to be plus 1. N1 becoming 0, probability is 1 by 2. N2 becoming plus 1, probability is 1 by 4. So R1, 1, R2, 0. If that has to be received, the probability of that event is 1 by 8. 1 by 8. And likewise, this will be 1 by 16. And you can continue, you will get 1 by 8 impulse here. I will not draw it, otherwise I will end up drawing so many lines here. 1 by 8, 1 by 4, 1 by 8, 1 by 16, 1 by 8, and 1 by 16. So you can, if you add up all these strengths, you should get 1, because it is a density function. So this is the conditional density function. This is how the conditional density function looks like. You will have 9 impulses, and it is a two-dimensional density function. Similarly, you can plot, please do this as an exercise. Similarly, you can plot conditional density function of R given H0 is the true hypothesis. Now here what happens is you will have it on this side, on this, in this quadrant. While in this case you had it in this quadrant, you will have it in this quadrant. You will have those impulses here. Now clearly the observation space in this case, is two-dimensional. So symbolically I will show like this. The observation space is two-dimensional. The possible values which the vector R can take were here earlier. So 0, 0 is a possibility, 1, 0 is a possibility, 2, 0 is a possibility, and so on and so forth. So there are 18 possible values, isn't it? There are 18 possible values which R can take. 9 possible values when H1 is the true hypothesis, and similarly another 9 possible values. 0 is common, of course. Another 9 possible values when H0 is the hypothesis. So altogether these points constitute the observation space in this case, which is two-dimensional. Observation space. So symbolically I'll just show it like this. So this is the discussion on the basic model of a detection problem. We have not yet discussed the decision rule, but we have understood what is a hypothesis source, what is meant by a probabilistic transition mechanism, and what is the observation space. Now on the observation space, the decision rule has to work, and a decision has to be taken with the decision rule. So the real task of an engineer here is to formulate a decision rule based on whatever information is available. So there are some more additional information is there which may or may not be available. So that we will discuss next when we discuss the decision criteria.